So in today's screencast, we're going to be talking about rate laws. And so far in our kinetics chapter, we've qualitatively described ways that we can affect the rate of a reaction. For instance, if we increase the concentration of a solution, then you're going to see more collisions happen per unit time. If we increase the surface area of a reaction, we know that the reaction is going to happen more quickly because there will be greater access to the molecules that need to collide. But all of that is qualitative, and when we're looking at wanting to be precise, we want to use some quantitative methods in order to really get down to the details of a situation. So we're going to mathify things today. So what has been done is an equation called a rate law was developed, and that is a way for us to express how the concentration of reactants might affect the rate of the reaction. So for example, if I have a reaction A plus B, where A and B are any reactants, just simplifying it here instead of putting formulas. If A and B go to react to make products, then the rate law looks like this. We say that the rate is going to be proportional to both the concentration of A and B raised to some exponent, N and M, which we're gonna figure those out today, and that's part of what needs to be done when determining a rate law. Now, you may remember in grade 11, or even possibly this year, we discussed how it is that you take a proportionality statement and you convert this whole thing into an equation, so we can change that proportional to an equal sign. And if you do remember that, you'll recall that we said, well, we add in a proportionality constant. And so in this case, it's this guy right here, K, which is referred to as the rate law constant. So maybe we should write that in, I'm thinking. Oopsies. There we go. So let's write that in. So K is our rate law constant. There we go. And so again, remembering what I said about N and M, those are just the exponents that are attached to the concentration values, and we're going to determine those experimentally. So just a reminder for you guys that whenever you see a particular molecule in those square brackets like that, that just means we're talking about their concentration, most often in moles per liter. So let's move on to going through how it is that we can determine the exponents, those at N and M value in our rate law. Now, there are ways to use calculus to do that, but of course that's beyond the scope of this course, and we can't assume that you have that prior knowledge. So I'm going to teach you a way to look at data collected from an experiment, rate law data, rate data, and that will help us to figure out what those exponents need to be. For those of you that have studied logarithms in your grade 12 functions course, you can certainly use logarithms to solve these problems as well. That's perfectly acceptable, but I can't assume that prior knowledge either. So we're going to proceed with this method. So in math, the way that you determine the order of a polynomial is by looking at the term with the highest exponent. In the rate law, we don't simply look at the highest exponent. We look at the sum of the exponents in the rate law. So for example, and this is purely just an invented example, if I said that the rate was equal to my rate constant times the concentration of some reactant A to the exponent 2 times the concentration of reactant B to the exponent 1, I know that the order would be just the sum of those exponents, the 2 and the 1, so my order would be 3. Right, 2 plus 1 equals 3. So it's pretty simple. All you're doing is really just adding up those exponents. So if you see a question like that, it's a nice easy mark for you, as long as you remember how to do it. Okay, so what we're going to do next is look at some data. So what you have before you is data relating to the initial concentrations of reactant A and reactant B in moles per liter. Always take a look at those units to make sure that you understand what they are, because we're going to be doing some unit analysis in this process. And then we're going to look at the initial rate of formation of products. Now, of course, we know that the initial rate is going to be much faster than as you go on, because for example, if you have a reaction, it's usually going to be pretty quick at the beginning, but then it's going to peter off as fewer and fewer reactants are available to collide and produce products, right? So that rate will typically go down over time. But we're only looking at the initial rate, concentrations and rates. Okay. So in order to examine this data, what you want to look for is you want to look at how each reactant is affecting the rate of the reaction, but you want to look at it in a controlled fashion. So for example, if I want to see the effect of reactant A on the rate, modifying the amount of concentration of A on the rate, then I need to make sure I'm controlling the change in reactant B. So for instance, I can't change the concentrations of both A and B and expect to give me any meaningful information about how each is affecting the rate. So for that reason, what I'm going to be looking for is I'm going to be looking for cases where the concentration of one reactant is changing in some fashion, but the other reactant's concentration is remaining stable. So when I look at this, what I see here is, I'm going to say from experiment 1 to experiment number 2, my concentration of A is doubling, and my concentration of B is remaining the same. So that provides me with a good opportunity to see what the effect of A is on my reaction rate, because only A has been changed. So let's look at what the effect is. So it looks like when I double the concentration of A, so I'm going to write times 2, and I go ahead and I look at what's happening during that same change in my reaction rate, then I'm seeing that my rate is also doubling. So when A doubles, so does the rate of the reaction. That's what I'm seeing here. So let's go back to our rate law proportionality statement. I know that the rate is proportional to the concentration of each reactant, right? It's not equal to, but it's proportional to the concentration of A raised to some exponent, right? So that's definitely true. If I've changed A, and that affected the rate. So that is a true statement. The unknown here is this business about how it changes it, and in what way. Is it linear? Is it quadratic? Is it cubic, etc.? So I'm going to sub in some values here. So let's just look at this. Well, I saw that when I doubled my concentration, hence the 2, I found that my rate doubled, right? So again, I doubled my concentration and my rate doubled. And so my job here is to figure out, well, what does the value of n have to be to make the left side of this situation equal to the right side? 2 to the power of n. Well, what does n have to be? The only way this works is if n is a 1. So that allows me to conclude that the value of the exponent n is 1. So I'm going to let you know that the trickiest part of this whole lesson is going to be the analysis of the data and then remembering how to determine how that data influences the value of that exponent. So we're going to go through and look at B next, but we're not quite done. So now we would say the reaction is considered first order for A, in that the exponent n is 1. So now we're not done. We need to look and see the effect of reactant B and its changing concentration on the rate. So let's do that. So just a reminder again, when we're looking at data, we want to see the effect of one reactant on the overall rate when the other reactant remains, its concentration remains stable. So, I could look at when there are a couple spots here where I could look, but I'm going to kind of point this out to you. So I can see first off that, right here in reactant B, between the third and fourth trial, what I've done is I've doubled my concentration. And what I need to double check with my other reactant A here is that its concentration is remaining unchanged. And that again allows me to ensure that whatever is happening to the rate is a function of changing reactant B's concentration and A is not influencing that rate change at all. And so let me go ahead and take a look at, well, what is happening to my concentration of my products. And so these numbers are not terrible. Sometimes the numbers are not ideal. So I just want to go through with you, well, what if the numbers are not very pretty? How do I figure out what the change is? So, I can always just take the second value and divide by the first. So for instance, the way that I got that the reactant, the concentration of B was doubled was I really just said 0.20 divided by 0.10, and that gives me 2. Those numbers, it's very easy to see. So I'm going to do the same thing over here. I'm going to do it in green with my reactants, or my rate rather, right? So I'm going to say, well, what is 2.40 divided by 0.60? And I know very quickly that that is going to give me a 4, right? 24 divided by 6. But again, the numbers aren't always really super pretty. In this case they were, but if they're not, that is the way that you can sort of go through and find out what the effect of the change in concentration is. All right, so I just want to take a minute then to remind us how this all works. So we saw that when the concentration of B doubles, then our rate quadruples, right? So let's go back to that basic rate law equation. We know that the rate is proportional to the concentration of B raised to some exponent m, and our job is to figure out what that value for m is, right? So again, I know that, well, what did I do? Let's think about what we did here. I doubled the concentration of B. And I want to see, well, how did that affect the rate? Well, the rate got, quadrupled. So, now I want to say, well, what is the only way that the left side here equals the right side? Well, that's if the value of m is a 2. 2 squared equals 4. So the value of m has to be a 2. So what does that mean? That means that our rate is second order with respect to B. So the reaction is second order with respect to B. So we're in pretty good shape here. We figured out what our values are for both n and m, the exponents in our rate law, but we're not quite done. Let me explain to you what I mean. So far where we are is we know that the rate law is this thing right here, and we can now say with a certain amount of certainty that we can include those exponents, the values determined for n and for m in our rate law. But like I said, we're not done because we still haven't figured out what this constant is, right? Our rate law constant, which by the way is unique for every individual reaction. So with each rate law question, you will need to determine the unique value for that rate law constant. And so how do we do that? Well, it's actually quite simple. What we need to do is we need to simply substitute in the rate and concentration data from our table earlier. So let me just go back and swing back and find that. Right, so I can use any line that I want to in my rate law data, my just experimental data, and so here's what I'm going to do. I'm just going to use this first line because I'm looking at the values and they look pretty straightforward, 0.10, 0.10, and 0.20, and so now I'm just going to go back to the spot where we did that. There we go. So, all right. Okay, so my rate, oops, is equal to K times the concentration of A times the concentration of B squared. And I'm just leaving out the one, well, let me just put it in. There we go. So remember that the rate was 0.20 moles per liter per second. K here times the concentration of A when the rate was 0.20 was 0.10 to the power of 1, and then 0.10 squared. And you'll find that when I divide out the 0.10 times the 0.10 squared, that the value, when I do that on both sides, the value that I get for K is 200. So again, all that I did in order to get the value for K was to sub in the data from the experimental results back into that rate law equation once I find out the exponents in the rate law. Again, though, I'm not done, because just as every value, just as every reaction has its own unique K value, the units for K are also going to be different. And so that is our next and final step in the process of determining the rate law for a given reaction, is to determine the units for the K value for that given reaction. So let's do it. So I may need to stop and sort of remind you of some basic ideas relating to math and fractions as we go through this, but we're essentially going to be using dimensional analysis to determine our units. So let me just start by writing out our rate law. So I know my rate is equal to K times the concentration of A times the concentration of B squared. But remember, I'm trying to find out the units for K, so I'm going to isolate K in this equation, and what I get is the rate divided by the concentration of A.
We have a call for RJ, the custodian.
And the concentration of B squared. There we go. And so now all I need to do, and this is how the units for any equation are basically determined, is you go ahead and you sub in the given units and you see what comes out. So I remember that the rate in this particular set of data, the rate was measured in moles per liter per second. And so I'm going to divide that. The units for A were moles per liter, and the units for B were moles per liter, but that, B is squared, so I'm going to put the squared in there. Okay, so I'm going to just simplify this a little bit by saying moles per liter per second divided by moles per liter cubed. And now this is where I'm going to remind you of some elementary kind of level math, right? Which is, where should I do this? I think I'll just kind of do this on the side over here. So you'll remember if you were dividing fractions, right? Which is essentially what we're doing here. We're just dividing a fraction, right? Moles per liter per second is a fraction, and then we're dividing it. So I'm going to, if I'm doing that, and I had, 1/2 divided by 3/4, in order to, be able to work that out, I would need to take the second fraction, invert it, and multiply. So we're going to do a little bit of that in the next step. So, so stay tuned. So the first thing I'm going to do is I'm going to rewrite this statement as a more as a division statement. So moles per liter per second divided by moles per liter all cubed. There we go. Let me make a little bit more room here. Let's see if I can do this. There we go. So now what I'm going to do is I'm going to invert and multiply. So I have moles per liter per second times, now I'm inverting that second fraction, liters, and I'm going to also distribute that cubed in the same step here, per moles cubed. And now I have a situation where I can cancel out some units. So I know liters cubed, right here, divided by liters, one factor of liters will cancel out. So I'm going to go ahead and just show that. That liter's gone, and now I'm left with only 2 factors of liters. I'm going to do the same thing with my moles. This mole on top will divide out with 1 factor of moles on the denominator, and that leaves me with 2 factors. So now I'm going to go ahead and simplify that. Well, what am I left with in the numerator? I'm left with liters squared. And in the denominator, I'm left with moles squared, and then my seconds. So the units for K are liters squared per mole squared seconds. So if I were representing this rate law in, let's say, a lab report or simply as an answer to a problem, I would say, therefore, the rate law is rate is equal to K times A, the concentration of A times the concentration of B squared, where K is equal to 200 liters squared per moles squared seconds. And that's it. All right, let's look at a second example. So here's our second example. So if you're feeling confident enough, you may wish to attempt this problem and then see how you did afterwards by pausing the video, but I'll leave that up to your own sort of comfort level at this point because we do have a third example. Let me just move this up a smidge so we have a little bit more space. So if you want to do that, go ahead and pause the video now. Otherwise, I'm going to kind of go through this question. All right. So first off, I usually start by writing out what my rate law is for a given reaction. And in this case, again, I've chosen to use just C and D as representative reactants, but you may see formulas for actual molecules there or elements. So let me write out my rate. So I know that my rate law is that my rate is equal to K times the concentration of C to some exponent N times the concentration of D to some exponent M. And so our job is going to be to figure out what those exponents are. So I'm just going to kind of leave some space here for some thinking. And let's take a look at our data. So again, I want to look at how the effect of changing one reactant affects the rate while the other reactant's concentration is stable. So it appears to me that I can look at between experiment 2 and 3, I can see that the concentration of C is tripling. And when I look at the concentration of D, I'm just double checking that concentration is remaining stable, so I'm good. But take a look at this. My rate does not change at all. So that's an interesting situation. So by tripling the concentration of C, there is no effect on my rate whatsoever. So let's go back to those basic ideas that we talked about in the last example, where remember I'm saying my rate is proportional to the concentration of C to some exponent N. Well, what did I do? Well, I tripled my concentration, and I want to know what N is, and my rate stayed the same. It was multiplied by 1. I can think of it as multiplied by 1. So my job is right now to say, well, what is the only way, what does N have to be in order for the left side of this expression to be equal to the right side? And, the only way that works is if the exponent is a 0, right? Anything to the power of 0 will give you a 1. So, in fact, the value of N in this case is 0, and this is a 0 order reactant. This reactant has no effect. Doubling its concentration, tripling its concentration has no effect on the overall rate. We say that it is 0 order with respect to C. So far, I can go ahead and I can fill in that my rate is equal to K times the concentration of C to the exponent 0. Let's take a look at what is going on with our other reactant. So, let me see. I think I'm going to use the green for this. And maybe what I'll do is I'll just get rid of some of this business here just to clean it up. And then maybe I'll just use red anyway. Okay. So again, if I want to see the effect of D, I need to make sure of changing D's concentration, that is, then I need to use experiments where the concentration of C and all other reactants are remaining stable. And so between experiment 1 and 2, I have quadrupled the concentration of D, and the concentration of C is remaining stable, or controlled. Let's look at how the rate is affected. So it looks to me 0.08 divided by 0.02 also gives me 4. So going back to my basic ideas, I'm seeing that whatever I do to my concentration, the same effect, it has the same effect on my rate. So again, rate is proportional to the concentration of D to some exponent m. My rate is proportional to, let me just get rid of that. I saw that when I quadrupled my concentration, my rate also quadrupled. So what is the only way this works? Well, my left side equals my right side only if the value of m is a 1. So this is first order. So hopefully you're seeing that when I observe that whatever I do to my reactants concentration, I see the same result or same change in my rate, then that will be first order. So I'm going to go ahead and say, well, D, and then put my exponent 1. So I can even simplify things at this point, remembering that any value raised to an exponent 0 will just give me 1. I know that this whole value here, this whole part of the expression, c to the power of 0 will equal 1. I can kind of just eliminate it, and that simplifies my math. So rate is equal to K times 1 times the concentration of D to the power of 1. So although we've done most of the hard work, we're still not done, you'll remember, because we still need to find out the value of our rate constant for this particular experiment, along with its units. Okay, so let me see. I'm going to see if I can move this up a smidge. There we go. So you'll remember we get K by simply subbing in data from our experiment. So I'm going to get rid of some of this business here. And then choose a data set. So again, it doesn't really matter which of the data sets you use, but I think I'm just going to use experiment number 1's data and then sub that in. But we'll remember that because the reaction was 0 order with respect to C, that we really don't need to input C's data at all here. So let me go ahead and do that. So the rate is 0.020 which is equal to K times the concentration of D at 0.010, and that's to the power of 1, which I don't really need to include. So isolating K, I'm getting a value of K of 2, but remember that I have 1, 2 sig figs, and so I need to put that as a 2.0. So lastly, the last little bit of this that I need to do before I pull it all together is to determine the units for K. So in order to do that, I'm going to go back and I'm going to look at, well, what was my rate? My rate was this guy right here, once I removed that C at a 0 order. So if I rewrite that rate law isolating K, I get, oopsies, I get that K is equal to my rate divided by the concentration of D, right? So K is going to be equal to moles per liter per second, oopsies, divided by moles per liter. K is equal to, I'm going to rewrite that as a division statement, moles per liter per second divided by moles per liter. And I'm going to invert and multiply and cancel out my units. So moles per liter per second times liters divided by moles. So my moles cancel, my liters cancel, and I have seconds in my numerator, or my denominator rather, right? So when I cancel out my moles and my liters, I'm left with a 1, which we can't forget. So what does that give me in terms of units? I get 1 over seconds, or seconds to the negative 1, whichever you prefer. So overall, I can sum this up. Let me sum up my rate before I get on to the next example. Therefore, the rate is equal to K times the concentration of reactant D, where K is equal to 2.0 seconds to the negative 1, or 1 over seconds, whichever you prefer. All right, let's go on to a third example. So in this third example, again, I would really like for you to try aspects of it on your own and to see what you can do, what your understanding is so far. And if you get stuck, then just come back to the video. But again, if you're still not there, that's fine. Just follow along, and we'll see where you are with that. So pause the video now if you want to attempt the question. Otherwise, I'm going to begin. All right, so in this question, I've used some reactants. You can see that the reactants are the ones that are listed here, right? The concentration of the products in a reaction such as this have no effect on the rate. It's only the concentration of my reactants, not my products, because the products aren't there to have any effect on the initial reaction rate. So they're not listed, and that should make sense. And so I've got some data here that I can examine to help me determine my rate law. So overall, I am going to just move this up a smidge so that I have some space to work, and I'm going to write out my rate law. So the rate is going to be equal to K times the concentration of S2O8 to negative to some value n, some exponent n, times the concentration of I minus to some exponent m, and my job is to figure out what all of that is, all of the unknowns are. So let me see. I am seeing that between experiment 1 and 2, the concentration of iodide is remaining constant, whereas the concentration of my S2O8 2 minus is not. And so these numbers are not super pretty. So I'm not sure if you remember what it is that I said about what to do when the numbers are not pretty. You just take the second value or the larger value and divide it by the smaller. You can do the reverse, but it's nicer to work with bigger numbers. So this is, I'm going to use my little thinking on the side business. So I would say 0.22 divided by 0.15. And when I go ahead and I do that, the value that the quotient is, I'm getting 1.46. So I'm going to round that to 1.5 for significant digits. So I know that when so the change is times 1.5. Now I'm going to do the same thing with my rate. Again, these numbers are not super pretty, but I'm going to divide the smaller into the larger and see what that changes. And remember, I need to do the same, go in the same direction for both of those. So 1.70 divided by 1.14. Okay, so 1.70 divided by 1.14. I'm getting 1.49. So you'll notice that, there's a different number of sig figs here. Remember, this is experimental data. It's not going to be perfect all the time. And so I have to judge whether these two values, the 1.5 and the 1.49, are within the same realm of, like, like similar enough, right? Is that within the realm of reasonable experimental error? I think it is. So I'm going to write this rate as having changed by a factor of 1.5. So you'll remember in the last two examples, whenever we saw a certain change in our concentration that affected the rate by the same factor, that was a first order reaction with respect to that reactant. So far I'm going to go in and I can say that the rate is proportional to my S2O8 to negative to the power of 1. It's first order with respect to that reactant. Okay, and so now let me get rid of a little bit so that I'm going to erase some stuff here. It's not letting me. Okay, so next what I want to do is it's not erasing, so I'm going to just move on here. The next thing I want to do is I want to take a look at what is going on with my other reactant, my iodide. So I'm going to clear this out and leave myself some thinking space. So remember, I want to pick trials where one is changing and the other one is remaining constant. So when I look at this, I can see, well, S2O82 minus is staying constant, and then what I have is my iodide changing. But by what factor? So let me do a little bit of thinking here on the side. So I have 0.21 divided by 0.12. That's from the change from experiment 2 to experiment 3. And I'm getting 1.75. So I know that this is changed by 1.75. And I'm going to do the same thing with my reaction rate. I'm going to say 1.70 divided by 0.98. Okay, and that's giving me 1.73. So I'm comfortable that that is within the realm of experimental error, and that they have changed by the same factor. So that gives me the confidence to say, okay, well, that means this reaction is first order with respect to iodide as well. So now that I have my exponents for my rate law, I can go ahead and I can substitute in to determine the value of K, and I can also go in and determine the units for K. So I'm going to go ahead and do that. I'm just going to give myself a little bit more space here. I think I'm just going to use the first trial. So when the rate was 1.14 moles per liter per second, the concentration of S2O82 minus was 0.15 to the power of 1, and the concentration of I minus was 0.21 to the power of 1. So when I go ahead and do the math on that and solve for the value of K, 1.14 divided by 0.15 and 0.21, I'm getting to 2 sig figs 36. Oopsies, 36. I'm just going to double check that just to be sure. 1.14 divided by 0.15 divided by 0.21. Yeah, 36. Okay, good. So now I'm going to go ahead and also determine my units for this. So my K value is equal to my rate divided by the concentration of S2O82 minus to the power of 1 times the concentration of I minus to the power of 1. So that's going to give me moles per liter per second divided by moles per liter times moles per liter. And so simplifying this and rewriting it as a division statement, I've got moles per liter per second divided by, and I'm going to simplify that denominator to moles squared per liter squared, right? Moles times moles and liters times liters. And now I'm going to invert and multiply. So moles per liter per second times liters squared per mole squared. Now I'm going to see what I can cancel. I can cancel out one factor of moles, and I can cancel out one factor of liters. And so that will give me liters divided by moles seconds. So there I go. So I'm running out of a little bit of room here, but I can see that my rate is going to be equal to this guy right here, where the value of K is 36 liters per moles seconds. And I'm just about done this question. This question has a little bit more to it, because when I look at the fourth experiment, and this is actually one of the reasons we developed this rate law, is so that we can make predictions about what the rate of the reaction will be for experiments that we actually haven't done yet. So for instance, in this question, what they're asking us, once we have the rate law, is, well, if my concentration of my first reactant is such and my second reaction is such, what can I reasonably predict the rate of the reaction to be? And so, I've developed this nice, beautiful rate law that is a mathematical equation that relates the rate to the given concentrations. So my job now is simply to utilize it for its intended purpose. So I'm just going to create a little bit of a workspace here for myself so that I can do that. Here we go. And so that's really all I need to do. So I have this rate that is equal to, and I'm actually going to sub in the value for K because I'm going to be using that value. The value is 36 times the concentration of S2O8 to negative to the power of 1. Oops, let me just make that nicer. 1 times the concentration of iodide to the power of 1. So again, I want to solve for my rate. Given the concentrations is 0.10 moles per liter for each reactant, 0.10. And my exponents are 1, so I can put them in symbolically. And then solve. So solving for that, I get 0.36. And what are my units for rate? Moles per liter seconds. Moles per liter per second. And that is it. So now that my video is complete, my screencast is complete, I want you to go on Google Classroom and to work through the worksheet that I've posted for you to the best of your ability, and certainly we can regroup at the beginning of next lesson. In the meantime, if you do have any questions that you feel I would be able to clarify via email, feel free to email me and I'll do my best to answer.